Hey everyone, and welcome. So, if you're deep into your physics studies, you've definitely run into the Irodov problem book, right? It's kind of legendary for being tough but brilliant. Well, today we're going to tackle problem 1.63, a real classic that's going to help us nail the concept of static friction once and for all. By the time we're done here, you'll have a super clear method for any problem like this.
So here's our game plan. First, we'll get a really good handle on the problem setup. Then we'll break down every single force that's at play. After that, we're going to zoom in on the two most important moments, when the block is just about to slide up and when it's just about to slide down. And finally, we'll bundle all of that into a powerful toolkit you can use for pretty much any statics problem you come across.
All right, so first things first, let's really visualize the physical system we're working with here.
This setup is a cornerstone of mechanics. You see it everywhere. And for good reason. It's this perfect little puzzle that lets us see how gravity, tension, and especially friction all battle it out. We've got our block, M1, on the ramp, tied by a string to a hanging weight, M2. The whole question really boils down to what's keeping this thing from moving? And here is the core of the problem. See, it's not just asking a simple yes or no question like, will it move? No, it's way more interesting. It's asking for the precise boundaries. What's the exact mass ratio, M2 over M1, that's just enough to start pulling M1 up the ramp? And on the flip side, what's the ratio where M1 is just about to slide down? And then, what's that whole sweet spot in between where everything just stays put?
To solve this, or really any problem in mechanics, there's one step that is absolutely non-negotiable: the free body diagram. This just means we're going to isolate each of the masses and draw every single force acting on it. Let's start with our block on the incline, M1. First force is always the easy one, gravity. It's simple, it doesn't care about the incline, doesn't care about the rope, it just pulls mass M1 straight down toward the center of the Earth with a force of M1 times G, period. Now, the block isn't a ghost, right? It's not falling through the ramp. That's because the ramp is pushing back. That push is what we call the normal force. And the most important thing to remember about it is that it's always normal, which in physics is just a fancy word for perpendicular, or at a 90-degree angle to the surface. Okay, next up, we've got that thread. It's pulling on M1, trying to drag it up the ramp. We call this force tension, and it always acts along the line of the rope, pulling away from the object. Now for the hanging mass, M2. Its free body diagram is way simpler. You've got gravity, M2G, pulling it straight down. And you have the same tension, T, from the rope, pulling it straight up. And since the whole system is in equilibrium, meaning it's not accelerating, we know that the tension pulling up has to be exactly equal to the weight of M2 pulling down.
And here we go. This is it. The single biggest trap in this entire problem: static friction. So many people get this wrong because they think it has a fixed direction. It doesn't. Static friction is, well, it's clever. It's a reactive force. It only pushes as hard as it needs to, and it always points in the direction that opposes the way the object wants to move. So, which way does it point? The answer is, it depends.
So, to figure out our boundaries, we have to look at the tipping points. These are the moments where things are just about to happen. Let's start with the first case, the instant that M1 is about to get pulled up the incline because M2 is really heavy. Just think about it for a second. If this heavy mass M2 is trying to drag M1 up the ramp, what is friction going to do? It's going to dig its heels in and try to stop it, right? So it's going to point down the incline, fighting against that upward motion. And right at this tipping point, it's giving it all it's got. It's at its maximum possible value. Okay, let's walk through the math piece by piece. First, let's look at the forces perpendicular to the ramp. We've got the normal force pushing out and a component of gravity pushing in. Since the block isn't flying off or sinking in, those have to be balanced. So the normal force, N, equals M1G times the cosine of alpha. Got it? Now the interesting part, the forces parallel to the ramp. We have tension pulling up. And what's pulling down? Well, two things. The component of gravity pulling it down the ramp, that's M1G sine alpha, and our maximum static friction. At that tipping point, they're perfectly balanced. So T equals M1G sine alpha plus Fs. Now we just plug in what we know for T and Fs, do a little algebra, and bam, we get the upper limit for our mass ratio.
So we found our upper boundary. Now let's go to the other extreme. What's the absolute smallest M2 can be before M1 starts sliding down the incline all on its own?
And look what happens. Friction completely flips its direction. It does a total 180. Now the force of gravity is the one trying to win, pulling M1 down the ramp. So friction switches teams. It now helps the tension, pointing up the incline to prevent that downward slide. It's still at its maximum value, just in the complete opposite direction. This is the key.
The process here is almost identical, but with one tiny, crucial change. The normal force calculation? Exactly the same as before. But look at step 2, the forces parallel to the ramp. Now we have two forces pointing up, the tension and the static friction. They're working together to fight against that downward pull from gravity. So our equation becomes T plus Fs equals m1g sine of alpha. See that? The sign on the friction term flipped. That one little minus sign becoming a plus sign changes everything. We solve this, and we get the lower boundary for our mass ratio. Okay, deep breath. We've done the hard work. We've found the two tipping points, the absolute upper limit and the absolute lower limit. Now we can finally put it all together and answer all three parts of the original question. So here's the big reveal, the main takeaway. The condition for being at rest isn't one single magic number. It's a whole range of possibilities. If your mass ratio is bigger than that first value we found, M1 slides up. If it's smaller than the second value we found, M1 slides down. But for any ratio that falls in between those two extremes, static friction is perfectly happy. It just adjusts its strength to whatever is needed to keep the whole system perfectly balanced and perfectly still.
And if you go and check the solutions in the back of the Irodov book, boom! They match exactly what we found. This just shows you the power of being systematic. We didn't guess. We drew our diagrams, we carefully analyzed the boundary conditions, and the physics led us straight to the right answer.
So let's zoom out for a second. What's the big lesson here? Let's turn this whole process into a reusable strategy, a toolkit that you can pull out for any statics problem that gets thrown at you. This right here is your 5-step plan to victory. 1. Always, always, always start with a free body diagram. Don't even think about writing an equation until your pictures are drawn. 2. Break down your forces into components that line up with your coordinate system. 3, and this is the big one, remember that static friction is a variable. It changes to oppose whatever motion is about to happen. 4, find those tipping points by setting friction to its maximum value. And 5, realize that the at-rest condition isn't one point, it's the entire safe zone between those two tipping points. And to leave you with something to chew on, go back to those final equations we derived. Ask yourself, what if there were no friction at all? What if K was 0? What does that do to our range for being at rest? Does it get bigger, smaller, or does it disappear completely? Thinking through that will really show you just how incredibly important friction is for keeping our world stable. Thanks for diving into this with me.